Let me ask you something that sounds so simple you might think I am wasting your time. What does it mean to go fast? No, really. You are sitting in a car, driving down the highway at 60 miles per hour. What does that number mean? It means that in 1 hour you cover 60 miles of road. Fine, that is just a ratio. Distance divided by time. A child can understand it. A dog, if it had a speedometer, could understand it. So let me ask the next question. You are in that car going 60, and you throw a baseball forward at 30 miles per hour. How fast is the baseball going? 90, right? 60 plus 30. A 10-year-old gets this. It is so obvious that nobody even bothers to think about it. You just add the speeds together, and right there in that perfectly reasonable, perfectly obvious answer is where the universe has been hiding something from you, because that answer is wrong. Not wrong by a lot. At 60 miles per hour, the error is so unbelievably tiny that no instrument humans have ever built could detect it. But it is wrong, and the reason it is wrong will lead us to the strangest and most beautiful thing physics has ever discovered about the structure of reality. So let us start with this simple addition. You are on a train, a nice fast train moving at 50 miles per hour. You walk toward the front of the train at 3 miles per hour. Someone standing on the platform watches you go by and says, "That person is moving at 53 miles per hour. Makes perfect sense. Galileo figured this out. Newton used it. For 200 years, no one doubted it." This rule, this adding of velocities, works beautifully for baseballs and trains and bullets and everything you encounter in daily life. And it seems to work for one very deep reason. Space is just space, time is just time, and motion is just a matter of covering ground. If I go this fast and I add a little more speed on top, I just go faster. Simple. But then somebody discovered something that made the whole thing fall apart. Not a philosopher, not a mathematician sitting in a room thinking, an experimentalist, a guy with equipment. In the 1860s, James Clerk Maxwell sat down and wrote a set of equations describing how electric and magnetic fields behave. 4 equations. And when he combined them, something unexpected popped out. The equations predicted a wave, a ripple in the electromagnetic field that would travel through empty space at a very specific speed. He calculated that speed, and it turned out to be about 186,000 miles per second. That number matched the measured speed of light almost exactly. Maxwell realized light is an electromagnetic wave. That alone was one of the great moments in all of physics. Think about what it means. Electricity, magnetism, light. 3 things that seem totally unrelated, all unified by 4 lines of mathematics. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They leapfrog each other forward through empty space, and that leapfrogging ripple is what hits your eye and lets you see. The electromagnetic spectrum, from radio waves to gamma rays, is all the same thing, just different frequencies of this ripple. The light you see is a tiny sliver of a much grander phenomenon, and Maxwell found the key to all of it. But there was something else tucked into those equations, something much more unsettling. The speed that came out of Maxwell's equations did not depend on anything. It did not depend on how fast the source of light was moving. It did not depend on how fast you were moving when you observed it. It was just a number, a pure constant of nature, baked into the equations like the ingredients in a recipe, and that made absolutely no sense. Think about why. If I am on that train going 50 miles per hour, and I shine a flashlight forward, shouldn't the light be going at the speed of light plus 50 miles per hour? That is what Galileo's rule says. That is what your intuition says. That is what Newton's physics demands. But Maxwell's equations said, no, the light goes at the speed of light. Period. Not the speed of light plus anything, just the speed of light. 2 sets of laws, both incredibly successful, flat out contradicting each other. Most physicists at the time assumed Maxwell's equations must be missing something. Maybe light needed a medium to travel through like sound needs air. They called this medium the ether. And if the ether existed, then the speed of light in Maxwell's equations was the speed relative to the ether. Problem solved, except someone went and checked. In 1887, Albert Michelson and Edward Morley built one of the most precise instruments in the history of science. It was called an interferometer. The basic idea is you take a beam of light, split it in half with a partially silvered mirror, send the 2 halves in perpendicular directions, bounce them off mirrors, and bring them back together. When the 2 beams recombine, they create an interference pattern, bright and dark bands of light caused by the waves being slightly in or out of step with each other. The brilliance of this setup is its sensitivity. If one beam traveled even a tiny bit faster or slower than the other, the interference pattern would shift, and Michelson's instrument could detect a shift of less than 1/100th of a wavelength of light. That is extraordinarily precise. The idea was straightforward. The Earth moves around the Sun at about 18 miles per second. If there is an ether sitting still in space and the Earth is plowing through it, then light going in the direction of Earth's motion should be a little slower than light going perpendicular to it, just like swimming upstream versus across a river. The Michelson-Morley experiment was designed to detect that difference. The equipment sat on a massive stone slab floating in a pool of mercury so they could rotate it smoothly without vibration. They took measurements at different times of day, different seasons, different orientations. The expected fringe shift was about 4/10ths of a fringe. Easily within their detection capability, they found nothing. No difference at all. The fringe shift was less than 1/100th of what was predicted, essentially zero. Light went at the same speed in every direction, regardless of how the Earth was moving. They repeated the experiment. They improved it. Other people tried it with better equipment over the following decades. Same answer. No ether wind. No difference. The speed of light was the same in every direction. Michelson himself was disappointed. He considered the experiment a failure because it did not find what he was looking for. It took years for the physics community to realize that the negative result was the result. The absence of the ether wind was the discovery. This was a crisis. Real physics was colliding with real physics, and something had to give. For about 18 years, this problem sat there like a splinter in the mind of physics. Hendrik Lorentz, a brilliant Dutchman, proposed that objects moving through the ether physically contracted in the direction of motion, just enough to hide the ether wind from any experiment. Henri Poincaré in France was circling very close to the right answer. George Fitzgerald in Ireland had similar ideas. They were all groping towards something, but none of them were willing to take the radical step. And then, in 1905, a 26-year-old patent clerk in Switzerland looked at the whole situation and did something that takes either extraordinary courage or extraordinary naivety, maybe both. He said, "What if we just believe the experiments? What if the speed of light really is the same for everybody, no matter how fast they are moving? What if that is not a problem to be fixed, but a fact to be accepted? And what if Galileo's simple rule for adding velocities is the thing that has to go?" Here is what made Einstein different from Lorentz and Poincaré, who had most of the mathematical pieces already. They kept trying to save the old picture. They wanted space and time to stay the way Newton said they were, and they invented mechanisms, physical contractions, local time coordinates to explain away the experiments. Einstein said, "Forget the mechanisms. The experiments are telling us something about space and time themselves. Listen to them." His name was Albert Einstein, and the paper he wrote on the electrodynamics of moving bodies, submitted in June of 1905, changed the meaning of space and time forever. Einstein started with two postulates, just two. First, the laws of physics are the same in every reference frame moving at constant velocity. That one is not controversial. Galileo basically said the same thing. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. That second postulate is the bombshell. It sounds innocent, but follow it to its logical conclusion, and the universe rearranges itself. Here is why. Suppose I'm standing by the railroad tracks, and a train goes by at half the speed of light. That is absurdly fast, but just imagine it. On the train, someone turns on a flashlight aimed at the front wall of the car. They see the light go from the flashlight to the wall. Simple. But what do I see standing on the ground? I see the light leave the flashlight, but while the light is traveling, the train is also moving forward. So the light has to travel a longer path to reach that wall because the wall has moved ahead. It has farther to go. Yet both of us must agree that the light is traveling at the same speed. The person on the train measures the speed of light at 186,000 miles per second. I measure it at 186,000 miles per second. Same number. If the speed is the same, but the distance the light travels is different for the two of us, then something else has to be different too. Think about it. Speed is distance divided by time. If the speed is fixed and the distance is different, the only thing left that can adjust is time. Time itself must be running differently for the two of us. The person on the train, from my perspective, has a clock that is ticking slower than mine, not because the clock is broken, not because of some trick, Because time, actual physical time, the time between events, is not the same for everyone. It depends on how fast you are moving relative to me. Let me give you a concrete picture. Imagine a very simple clock. It is just two mirrors facing each other, with a pulse of light bouncing back and forth between them. Every time the light hits a mirror, that is one tick. On the train, the light goes straight up and down between the mirrors. Very simple, but from my perspective, standing on the ground, the train is moving. The light still has to go from the bottom mirror to the top mirror, but the top mirror has moved sideways while the light was in transit. The light has to travel a diagonal path. A diagonal path is longer than a vertical path. The light still goes at c, the same speed for both of us, so it takes longer to complete one tick. The clock on the train, seen from the ground, ticks slower. And this is not just one particular type of clock. It is all clocks. Mechanical clocks, atomic clocks, biological clocks, the aging of cells, the decay of radioactive atoms. Everything that measures time runs slower for the moving observer, because it is not the clocks that are slow. It is time itself. This is called time dilation, and it is not a metaphor. It is not an approximation. It is measured fact. We have clocks precise enough to detect it. Put an atomic clock on an airplane, fly it around the world, bring it back, compare it to an identical clock that stayed on the ground, and the traveling clock is behind, not by much, a few hundred nanoseconds, but by exactly the amount Einstein's equations predict. The global positioning system that helps people navigate relies on satellites carrying atomic clocks in orbit. Those clocks tick at a different rate than clocks on the ground, partly because of their speed, partly because of gravity, which is another story. If the engineers did not correct for relativistic time dilation, the positions the system reports would drift by several miles per day. Every time someone uses a satellite to figure out where they are relying on Einstein being right about time. Let that settle for a moment. Time is not universal. Your seconds and my seconds are not the same seconds if we are moving relative to each other. But it does not stop there. If time changes, space has to change too. This is not optional. It is forced on you by the same logic. When I watch that train go by at half the speed of light, I measure the train to be shorter than the person on the train measures it. The train, in my frame, is physically contracted along the direction of motion. This is called length contraction. The faster the train goes, the shorter it gets in my measurement. And I want to be very careful here. This is not an illusion. It is not like perspective, where things look smaller when they are far away. If I could somehow arrange a measurement, a real physical measurement of the length of that train as it passes, I would get a shorter number than the person riding on it. Space itself is being squeezed. People struggle with this, and I understand why. You want to ask, but who is right? Is the train really shorter or not? And the answer is there is no really. Both measurements are equally valid. Length is not a property of the train alone. It is a property of the train and the observer together, much like direction. North is not a property of the compass needle alone. It depends on where you happen to be standing on the Earth. This is the revolution Einstein brought, not just new equations, though the equations are beautiful, a new understanding of what measurement means, what objectivity means, what really means when you strip away assumptions you did not know you were making. So already we have lost two things we thought were absolute. Time is not universal. Length is not universal. Both depend on relative motion. Now let us push this further. What happens if we go back to our original question about adding speeds, but now we do it correctly? You are on a spaceship moving at 90% of the speed of light. You fire a missile forward at 90% of the speed of light relative to you. Common sense says 90 plus 90 is 180% of the speed of light. The missile should be going faster than light. But common sense is wrong because common sense was built on everyday experience where things move at negligible fractions of the speed of light. When you add velocities correctly using Einstein's formula, you do not get 180%. You get something like 99.4% of the speed of light. The formula is not complicated. If one thing moves at speed v and something on top of it moves at speed w, the combined speed is not v plus w. It is v plus w divided by 1 plus v times w over c squared, where c is the speed of light. At low speeds, v times w over c squared is practically zero, so the formula reduces to plain old v plus w. Galileo was right for slow things, but at high speeds that extra term in the denominator grows, and it prevents the total from ever reaching c. You can try any combination you like. 90% plus 90%, 99% plus 99%, 99.99% plus 99.99%, you will never reach 100%. You will always get something just below the speed of light. It is like a mathematical ceiling that you can approach but never touch. But I want you to ask a deeper question. Why? Why does the universe have this structure? Is the speed of light just some arbitrary speed limit, like a highway sign? Is there a cosmic policeman handing out tickets? No, it is much deeper than that. And to see it, you have to let go of one more thing you believe about reality. You think of the world as 3 dimensions of space and 1 dimension of time. Up, down, left, right, forward, backward, and time moving along separately, like a metronome ticking in the background. Space is the stage. Time is the clock. They have nothing to do with each other. That picture is wrong. In 1908, Hermann Minkowski, who had actually been one of Einstein's mathematics professors, stood up at a conference and said something extraordinary. He said, "From now on, space by itself and time by itself are doomed to fade into mere shadows. Only a kind of union of the two will preserve an independent reality." What he meant is this: space and time are not separate things. They are 2 aspects of a single entity called space-time. And just like you cannot understand the shadow of an object without knowing the object itself, you cannot understand space or time separately without understanding the space-time they both belong to. Let me try to give you a feeling for what this means. Think about directions. I am standing facing north. I say that wall is 5 feet to my left. You are standing facing east. You say that same wall is 5 feet in front of you. We disagree about the direction, but we agree about the distance. The wall is 5 feet away. Our measurement of left versus front depends on which way we happen to be oriented, but the actual distance does not. Something very similar happens in space-time, but instead of different orientations in space, we have different states of motion. When you move relative to me, it is like we are facing different directions in space-time. You slice space-time differently. Your space is tilted relative to my space. Your time is tilted relative to my time. That is why we disagree about lengths and durations. But there is something we always agree on, a kind of space-time distance that does not change no matter who measures it. It is called the space-time interval, and here is the remarkable thing about it. When you compute this interval, space and time do not contribute the same way. In ordinary space, if you go 5 feet forward and 3 feet to the side, the total distance comes from adding the squares, 5 squared plus 3 squared. But in space-time, space and time have opposite signs. The interval is the time part squared minus the space part squared, or the other way around depending on your convention. The point is that minus sign, space and time are not the same kind of thing. They are woven together, but they pull in opposite directions. And that minus sign is where the speed limit comes from. Let me explain this more carefully because it is the key to everything. In ordinary space, distances work the way Pythagoras told us. If you walk 5 feet east and 3 feet north, your straight line distance from where you started is the square root of 5 squared plus 3 squared. Both directions contribute positively. You can go as far as you like in any direction. There is no maximum distance in any direction. But space-time is not ordinary space. That minus sign between the space part and the time part changes everything. It means that space and time partially cancel each other, and this partial cancellation creates boundaries that do not exist in ordinary space. Think of it this way. In ordinary geometry, a circle is defined by all the points at the same distance from the center. It is a closed curve. Nothing special happens at any point on it, but in space-time geometry, the equivalent of a circle is a hyperbola, an open curve that sweeps out toward 2 asymptotes, 2 straight lines it approaches but never touches. Those asymptotes correspond to paths through space-time at the speed of light. The hyperbola divides space-time into distinct regions. Inside the hyperbola is the time-like region, where causes and effects live, where massive objects move, where the interval between events has more time than space. Outside the hyperbola is the space-like region, where no causal connection is possible, where no massive object can reach, where the interval has more space than time. The asymptotes themselves, the light cone, form the boundary. In ordinary space, there is no maximum distance you can go. You can go a mile, 10 miles, a million miles. There's no limit. But in space-time, that minus sign between space and time creates a boundary, a geometric boundary like the edge of a cone. That boundary is defined by paths where the space-time interval equals 0. And what moves along those paths? Light. light follows the boundary of the cone. It travels through space-time in such a way that the space part and the time part exactly cancel, giving an interval of 0. Anything with mass travels inside the cone, where the interval is positive, and nothing, absolutely nothing, can cross from inside the cone to outside the cone, not because of a force, not because of a law imposed from the outside, but because the geometry of space-time simply does not allow it, any more than the geometry of a sphere allows you to walk off the surface. So when people say nothing can go faster than light, that phrasing is a bit misleading. It makes it sound like there is a speed limit, and light just happens to be at the limit. The truth is that the speed of light is not really a speed. It is a conversion factor between space and time. It tells you how many meters of space are equivalent to 1 second of time in the geometry of the universe. And that geometry has a shape, and that shape has a boundary, and light lives on that boundary. You do not hit a wall when you try to go faster than light. You find that the question itself stops making sense, the way it stops making sense to ask what is north of the North Pole. But I know what you are thinking. You are thinking, fine, the geometry forbids it, but what physically happens if I keep accelerating? What stops me? Good question. Let us find out. Imagine you are in a rocket, and you have an engine that can push you forever. You accelerate at a comfortable rate, let us say the equivalent of Earth's gravity, about 10 meters per second squared. Very comfortable. You feel normal weight. You could eat dinner, read a book, live your life. After 1 year of this acceleration, you are moving at about 77% of the speed of light relative to Earth. After 2 years, 97%. After 3 years, 99.5%. You keep accelerating. You feel the same push. Your engine is working just as hard, but your speed, as measured by someone back on Earth, is barely increasing. You are stuck asymptotically approaching the speed of light, like a curve approaching a line it never touches. What is happening? Where is the energy going? This is where we need to talk about mass and energy, and I want to be precise because this is one of the most misunderstood ideas in all of physics. In the old days, people used to say that your mass increases as you go faster. Relativistic mass, they called it. The idea was that as you approach the speed of light, you get heavier and heavier. And that is why you cannot reach it, because you would need infinite force to accelerate an infinite mass. I never liked that way of talking about it. Your mass is your mass. The number of atoms in your body does not change because you are moving fast. What changes is the relationship between force and acceleration. At low speeds, a given force produces a given acceleration. At high speeds, that same force produces less and less acceleration. Not because you are heavier, but because the geometry of space-time distorts the relationship between energy and motion. The correct way to say it involves energy. As you accelerate, you are pouring energy into your motion. At low speeds, most of that energy goes into making you move faster. But as you approach the speed of light, more and more of that energy goes into something else. It goes into increasing your momentum in a way that barely budges your speed. The energy is still there. It has not disappeared. But it is not making you faster. It is piling up, so to speak, in the region just below C. And to reach C exactly, you would need infinite energy. Not a very large amount. Infinite. The energy of the entire observable universe would not be enough. You could harness every star, every galaxy, every particle of matter, convert all of it to propulsion, and you still would not reach the speed of light if you have any mass at all. That is not a practical limitation. It is a mathematical one. It arises directly from the structure of Einstein's equations, and those equations arise directly from the geometry of space-time. We see this in particle accelerators every day. At a place like the one in Geneva or Fermilab near Chicago, physicists accelerate protons to enormous speeds. They pour tremendous amounts of energy into these particles. A proton at rest has a certain mass energy, about 938 million electron volts. But in the largest accelerators, each proton carries trillions of electron volts of energy, thousands of times its rest mass energy. And the proton's speed, it is going at 99.9999% of the speed of light. Not quite c, never c. All that energy, thousands of times the proton's own mass energy, manages to push it from 99.99% to 99.9999%. The last tiny fraction of a percent costs almost everything, and C remains untouched, unreachable, like a horizon that recedes exactly as fast as you approach it. which brings us to the most famous equation in physics, E equals mc squared. And I want you to see it in a new light now. That equation does not just mean that mass can be converted to energy, although that is true and spectacular. It means something deeper. It means that mass is a form of energy. And energy has inertia. And that inertia, that resistance to acceleration, is what prevents you from reaching the speed of light. When a particle sits perfectly still, it has energy, not kinetic energy, because it is not moving, just energy from having mass. Rest energy, we call it. And that rest energy is equal to the mass times c squared. The speed of light squared appears as a conversion factor, turning mass into energy units. As the particle starts moving, its total energy increases. At low speeds, the extra energy is what Newton would have called kinetic energy, 1/2 mv squared, the old formula. But at high speeds, the total energy goes as mc squared divided by the square root of 1 minus v squared over c squared. As v gets close to c, that square root in the denominator gets close to 0, and the energy shoots toward infinity. So the answer to why cannot you go faster than light is this: because getting to the speed of light would require infinite energy, and infinite energy does not exist. The universe does not have enough. But wait, photons travel at the speed of light. How do they manage it? The answer is elegant and clean. Photons have no mass. Their rest energy is 0. They are born at the speed of light, and they travel at the speed of light, and they never travel at any other speed. A photon does not accelerate to c. It exists at c. It does not experience time. From the photon's perspective, if you can call it that, its entire journey from emission to absorption happens in a single instant, no matter how far it travels. This is not a metaphor. The time dilation formula tells you that at the speed of light, time dilation becomes infinite. A clock moving at c would be frozen. The photon crosses the universe in no time at all, from its own frame. Of course, the photon does not have a proper reference frame in the usual sense, which is one of those subtle points that causes a lot of confusion if you are not careful. But the mathematics points clearly in that direction. So we have two classes of things in this universe: things with mass, which always travel slower than light and can never reach it, and things without mass, which always travel at exactly the speed of light and can never slow down. There is no gradual transition from one class to the other. You are in one or you are in the other. The geometry forbids crossing. Now I want to take you one level deeper, because there is something even stranger hiding in all of this. You know what causality is. It means that causes come before effects. You drop the glass before it breaks. You throw the ball before it hits the wall. This ordering, cause then effect, is not just a human convention. It is built into the laws of physics, and it is protected by the speed of light. Here is why. If nothing travels faster than light, then no information, no signal, no influence of any kind can get from one event to another faster than light can. This means that for any two events that are causally connected, where one influences the other, there will always be enough time for light to travel between them. All observers, no matter how fast they are moving, will agree on which event happened first. But if something could travel faster than light, this protection breaks down. And not in some minor academic way. It breaks down catastrophically. Because Einstein's equations of time and space are symmetric in a particular way. If you could send a signal faster than light in one reference frame, then there exists another reference frame moving at some high but subliminal speed, in which that signal arrives before it was sent. Read that again. If faster than light travel were possible, then from some observer's perspective, the effect happens before the cause. You receive the message before it was transmitted. You see the glass unbreak and fly back onto the table before it was knocked off. The entire structure of cause and effect, the thing that makes the universe comprehensible, collapses. Let me make this vivid. Suppose I have a faster-than-light telephone. I call you on planet X 10 light years away, and the signal gets there instantly. You immediately call me back using the same technology. From your reference frame, the signal travels instantaneously. But you are moving relative to me. Say you are on a spaceship. Relativity tells us that your now is different from my now. Your instantaneous reply, which is simultaneous with the reception in your frame, can arrive in my frame before I made the original call. I pick up the phone and hear my own message coming back before I have sent it. I could then choose not to send it. But if I do not send it, how did I receive it? This is not a cute puzzle. It is a logical contradiction, a paradox that the universe cannot resolve. The only consistent resolution is that the faster-than-light telephone cannot exist. This is not a proof, exactly. Nature does not owe us causality, but every experiment we have ever performed is consistent with causality holding everywhere, and the speed of light being the boundary that enforces it. If you want to throw away the speed limit, you have to be willing to throw away cause and effect. And so far, nature has shown no appetite for that trade. Let me step back and collect what we have built. We started with a child's question. What does it mean to go fast? We found that the obvious rule for adding speeds together is a lie, a very good approximation at low speeds, but fundamentally wrong. We traced the problem to Maxwell's equations, which demanded that the speed of light be universal. We followed Einstein in taking that demand seriously and watched as time dilation, length contraction, and the relativistic velocity addition formula all tumbled out. Then we went deeper. We saw that space and time are not separate things but components of a unified spacetime, and that the geometry of spacetime has a built-in structure, a cone of light that divides the universe into what can be reached and what cannot. The speed of light is not a traffic law. It is the geometry of existence. We saw that reaching the speed of light would require infinite energy, not because of friction or drag, but because the relationship between energy and velocity curves upward without bound as you approach c. We saw that massless things like photons live on the boundary, and massive things live inside it, and there is no crossing over. And finally, we saw that this speed limit is not just a constraint on motion. It is the guardian of causality. Without it, effects could precede causes, and the orderly chain of events that makes physics and life and thought possible would unravel. You might wonder, if all of this is true, why does the world not look relativistic? Why does everyday life feel Newtonian? The answer is simply that you are slow. I do not mean that as an insult. Everything you have ever encountered is slow compared to light. The fastest human-made objects reach maybe a few thousandths of a percent of the speed of light. At those speeds, time dilation and length contraction are so tiny they disappear into the noise. Galileo's velocity addition works to extraordinary precision. Newton's mechanics is flawless for practical purposes. But that does not mean relativity is some exotic curiosity that only matters in particle physics laboratories. It means that the world you experience is a slow-motion approximation of a deeper reality. You are living inside a narrow slice of what is possible, and the rules of that slice happen to be very simple. Step outside it, go faster, and the simplicity dissolves, and you see the real structure underneath, the real structure, the one with space-time geometry and light cones, and the interweaving of space and time is always there. You just cannot notice it at walking speed. Now, let me be honest about what we do not know. There is a hypothetical particle called a tachyon, a particle that would always travel faster than light, just as photons always travel at the speed of light, and ordinary matter always travels slower. Tachyons have been imagined and mathematically explored since the 1960s. In the equations, if you let a particle have imaginary mass, meaning the square of the mass is negative, then the math does produce solutions that go faster than light. But here is the crucial thing. No one has ever observed a tachyon. No experiment has ever produced one. No theory that includes tachyons has managed to avoid the causality violations I just described. Every time physicists have found something that looked like it might involve faster than light effects, it has turned out, on closer inspection, to be something else. Quantum entanglement, for instance, involves correlations that appear instantaneously across any distance, but you cannot use entanglement to send a message faster than light. The correlation is real, but the information transfer is not. So as far as we know, the speed of light stands as an absolute boundary, not as a guess, not as a suggestion, but as a consequence of the fundamental geometry of the universe we inhabit. There is one more thing I want you to see before we close, because it ties everything together in a way I find deeply moving. We talked about time dilation as a consequence of the speed of light being constant. Let me show you that this is not just a theoretical curiosity. It is confirmed by nature in a beautiful way. High in the atmosphere, about 10 miles up, cosmic rays from deep space slam into air molecules and create particles called muons. Muons are like heavy electrons. They are unstable. A muon at rest decays in about 2/millionths of a second. That is its lifetime. 2/millionths of a second. Even traveling at 99% of the speed of light, a muon should only make it about 600 meters before it decays. not nearly far enough to reach the ground from 10 miles up, and yet we detect muons at ground level. Lots of them. They are raining down on you right now. How? Because the muons are moving so fast that time dilation stretches their lifetime. In our frame, the muon's internal clock is running slow. Its 2/millionths of a second lasts much longer, according to our clocks. Long enough for it to travel all the way to the ground. From the muon's perspective, something different but equally valid is happening. The muon sees itself living for a perfectly normal 2/millionths of a second, but it sees the distance between the upper atmosphere and the ground as length contracted. The 10 miles of atmosphere is squashed down to just a few hundred meters. So the muon easily covers the distance in its short life. Both descriptions are correct. Both give the same prediction. The muon arrives at the ground, relativity is consistent, and nature confirms it with every muon that reaches your feet. That is what makes this physics, not philosophy. The predictions are specific, the measurements agree, the theory is tested billions of times a day by particles that do not know and do not care about human opinions. And that is what I find most astonishing about this whole business. It is not a rule that someone imposed. Nobody decided that 186,000 miles per second was a nice round number and slapped a limit on the universe. The limit emerges naturally from the shape of space-time. The universe is built this way. The fabric of existence, if you want to be poetic about it, has a weave, and the weave has a maximum angle, and that maximum angle corresponds to the speed of light. If you change the speed of light, you do not just change how fast things can go. You change the geometry. You change the relationship between space and time. You change how energy relates to mass. You change how gravity works. You change the size of atoms. You change whether stars can form, whether chemistry can happen, whether complex structures can exist. The speed of light is not just a number. It is a thread that, if you pull it, unravels the entire tapestry. There is a beautiful way to see this. Think about the formula C equals 1. In the system of units physicists sometimes use called natural units, we set the speed of light equal to 1. Not 1 mile per second, not 1 meter per anything, just 1. When we do that, the equations of physics become cleaner. E equals m, not E equals mc squared, just E equals m. Because mass and energy are the same thing, measured in the same units, once you stop using an artificial distinction between meters and seconds. In these units, the speed of light is not some big impressive number. It is the most boring number imaginable. 1, it is the identity, the conversion factor that says space and time are really the same stuff, just measured with different rulers. And the reason nothing goes faster than 1 is the same reason nothing in ordinary space goes farther than 1 in a direction that only has 1 unit. It is a geometric constraint. It is like asking why you cannot walk more than 360 degrees around a circle. You can walk as far as you want, but the geometry brings you back. I find this extraordinarily satisfying. We started with something that seems like an arbitrary prohibition. Nothing goes faster than light. It sounds like a parent saying, "Do not touch the stove." But when you dig into it, you find that it is not arbitrary at all. It is necessary. It is built into the architecture of reality at the most fundamental level. The universe is not forbidding you from going faster than light. The universe is showing you its shape. And in that shape, the question of going faster than light is like the question of going north from the North Pole. It is not forbidden. It is meaningless. There is no north from the North Pole. There is no faster than c in space-time. Every now and then someone comes along and says, "But what about warp drives? What about wormholes? What about expanding space?" And these are legitimate questions. In general relativity, which is Einstein's theory of gravity, space itself can stretch and compress. During the very early universe, the distance between points in space increased faster than light, not because anything moved through space faster than light, but because space itself was expanding. Galaxies far enough away from us are receding at faster than the speed of light right now for the same reason. But this does not violate relativity. The speed limit applies to things moving through space, not to the expansion of space itself. No information is being transmitted. No object is locally exceeding c. The space between things is just getting bigger. It is a subtle but crucial distinction. Locally, at every single point, nothing moves faster than light. The apparent faster-than-light recession is a cumulative effect of many small patches of space, all stretching a little bit. As for warp drives and wormholes, there are solutions to Einstein's field equations that describe these things mathematically. The Alcubierre metric, proposed in 1994, describes a bubble of warped spacetime that could in principle transport a region faster than light. Space contracts in front of the bubble and expands behind it, carrying the bubble and everything inside it forward. The occupants feel nothing. Locally, they are stationary. It is space that moves around them. Sounds wonderful. But every such solution requires exotic matter with negative energy density, something we have never observed in the quantities needed and may not exist at all. There are also severe problems with the energy requirements, which some calculations put at more than the mass energy of the entire observable universe, though later work has reduced that somewhat. And there are theoretical arguments that the bubble itself might be impossible to create from the inside. These remain beautiful speculations, not technology, not even close to technology. They tell us something about the richness of general relativity as a mathematical framework, but they do not change the fundamental message. Locally, the speed of light is king, so where does this leave us? We live in a universe with a speed limit. That speed limit is not a law imposed from outside. It is the geometry of the world from the inside. Space and time are interwoven in such a way that there is a maximum rate at which causal connections can propagate, and that rate corresponds to what we call the speed of light. Anything with mass is forever confined to the interior of the light cone. The boundary is absolute, and yet within that boundary the universe manages to produce galaxies, stars, planets, oceans, trees, brains, and conversations about the speed of light. The constraint is severe, but the creativity within it is infinite. I think there is a lesson in that, though I am not sure I can put it into words precisely. It is something like, the deepest truths about nature are not the things you can do. They are the things you cannot do. The places where the universe says no, where it draws a hard line, those are the places where you learn the most about what the universe actually is. The speed of light is one of those lines, and if you sit quietly with it, if you let the mathematics settle into your bones, it stops feeling like a limitation. It starts feeling like a window into the shape of everything. What is the one thing about this that you find hardest to believe? I have told you what I think. Tell me what you think, and let us see if we can get any closer to the truth together.